Good afternoon and welcome to MOS Live. Today we are doing Ask a Scientist all about lightning. My name is Katie, my pronouns are she, hers, and I'm going to be your moderator today, keeping an eye out for all of your questions. So if you're on Zoom, you can head to that Q&A button at the bottom of the screen and type in your questions to our educators about lightning. And if you are on Facebook or YouTube, thank you so much for joining us, but unfortunately we cannot see your comments at this time. If you'd like to see closed captioning, please head down to the bottom of your screen as well. That button may look like a CC, and you can see closed captions there. So at this point, I'd like to invite our educators to turn on their cameras and introduce themselves.
Hi, I'm Chuck. My pronouns are he and him and his. And one really interesting fact about lightning is that it can occur during the winter, which a lot of you may be wondering why we're having a lightning talk as we're going into winter, but it can occur during winter storms.
Hi, everyone. My name is Eric. My pronouns are he, him. And my favorite thing about lightning is that it can occur in places you might not expect, like on a volcano. When you have a lot of ash coming out of the volcano, it can cause a similar effect to what you see in a big thundercloud, and you can get discharges of electricity that are beautiful lightning displays of lots of different colors because of the interesting gases coming out of the volcano.
Hi, everybody. My name is Karen, and I think one of my favorite things about lightning is on a really hot summer's day when thunderstorm rolls through, you get an amazing light show, an amazing sound show, and then the air just feels so much crisper and cleaner after that. So that's one thing I love about lightning.
Great, thank you everyone. So our first question is, where does lightning come from? You've talked a little bit about weather. Is it related to that?
It is a good place to. I was going to say a good place to start is just establishing what are electric charges, because we will most definitely be talking about electric charges in our time together today. So I'll do a brief overview, and then Chuck, if you want to add to that, because it sounded like you were getting ready to say something. There are two types of electric charge out there in the world. We have positives and we have negatives, and everything is made up of charge. You, me, the sandwich you eat for lunch, the lightning cloud is made up of electric charge, everything. Typically, everything is balanced. So there's the same amount of positive and negative charge. Now, these charges, if they are opposites, like a positive and a negative, will pull towards each other. They will attract. If they are the same, like two negatives, they will repel or push away. And this is essentially what leads into the creation of a lightning bolt, whether on a giant scale, like coming from a lightning cloud, or on a much smaller scale, like coming from your fingertip to your pet dog or your doorknob. And it's all about when those charges get unbalanced. So if you have a lot more of one type of charge in one place, those charges are going to attempt to rebalance. And when it moves through the air, it happens to light it up, make a lightning bolt, either teeny tiny or ginormous.
So one of the things you really need to get lots of big lightning displays like we get in thunderstorms, or as Eric mentioned, in volcanic ash clouds, is you need to get a lot of one kind of charge separate from a lot of another kind of charge. You need to have regions where there's a whole lot of positive, regions with a whole lot of negative, and they will attract a force on each other and try to get together. That happens in a volcanic cloud because as it's very turbulent, because the volcano is emitting lots of gases, very hot, rising very fast. You get a lot of turbulence. And as we see here in this screen, we can see that lightning charges often result from that. As you may know, if things rub together, you can get electric charge. When you scuff your feet across a rug on a dry, crisp winter's day and then try to touch a metal doorknob, you'll get a tiny lightning discharge to your finger. In the same way, in thunderclouds in the summertime, you've got lots of ice particles. It's very cold in the upper part of these tall thunderstorm clouds. It's very cold. You got lots of ice and snow there. They rub up against each other, and through a mechanism we don't really understand all that well, we get huge amounts of electric charge, what we call potential, voltage potential, lots of positive, and another area where there's lots of negative, and then you get potential for some lightning displays.
Thanks. So I was just going to ask if those mini little shocks I get in my home are like mini lightning, but it sounds like, since it's all electrical charges, we're on the right track.
Yeah, and you might be surprised. It's not much current, so but it is a lot of voltage. Those discharges can be over 1,000 volts, but the current is so small that it doesn't really hurt you. You just no, you just notice it, but it's not a lot of current.
Aptly named shock in that case. You just get a little, oh, that happened. So we're talking about electrical charges and how this all works nearby. Can lightning exist on other planets?
Definitely. Where we have other planets that have atmospheres similar to the Earth, we have seen evidence of lightning there. Jupiter, Saturn are gas giants, which means they're nearly all atmosphere. And we've seen evidence of lightning happening there, which dwarfs all of the lightning on the Earth. It makes an Earth lightning bolt in a storm seem like a tiny little shock you get from touching a doorknob. They're that huge. They might be hundreds of miles. They're constantly happening. Jupiter, Saturn, and even Uranus and Neptune further out are famous for their giant storms, and they definitely include a lot of lightning. Venus and the inner part of the solar system also has a super thick atmosphere, about 100 times our own, and it has sulfuric acid rain, and it's extremely hot, and probably a good deal of lightning there too with all the turbulence.
And Mars as well with its dust storms. Potentially you could get lightning bolts. I'm not exactly sure of the data on how much has actually been recorded, but the physics seem like you could have them that way too.
Are there different types of lightning, like different names to all these scenarios you're speaking of?
They all sort of have the same basis of you get these electric charges moving through a gas, and it basically illuminates that gas. When it moves through the air, you may have noticed that different lightning that you might see might appear different colors. Most of the lightning that we see out in nature, or even in our Theater of Electricity at the Museum of Science, if you visited and seen our lightning show, it's sort of a bluish, purplish white. And that has to do with just the composition of the gases that are in the air around us. Whereas if you were to run electrical current, so those electric charges through a single gas like neon, you're going to get a bright red illumination. Or as Eric was pointing out, on these different planets with their different composition of gases, you're going to get other colors of lightning. But I think we here on Earth would still call it lightning. It would just be referred to maybe as space lightning or playground slag lightning or put your doorknob lightning. You'll probably come up with lots of different names, but essentially it's all stemming from the same point: unbalanced charges moving through gases trying to rebalance themselves.
Now, you may have heard of lightning called by different names. There's something called sheet lightning, for example, which is that where there doesn't appear to be a bolt, but a wide, diffuse area of the sky seems to light up. That's ordinary lightning, but the lightning bolt is being hidden either by clouds or by falling rain or hail between us and the lightning discharge. So that's why it looks diffuse. Then there's something called heat lightning. Is heat lightning different? No, heat lightning is ordinary lightning, but it occurs in a very distant thunderstorm, so far away that you can't hear the thunder. It's maybe 100 miles away or so. And it's called heat lightning because it often happens on hot nights before the thunderstorm arrives. And then there are other strange phenomena called ball lightning, which is another kind of electrical phenomenon which may occur during thunderstorms. And it's this pocket of electrically charged air that can drift around, caused also by electrical forces. So lots of interesting names that people have given it.
There's also, you make me realize there are sort of different names and types. Sprites are a type of lightning that happens really, really high up in our atmosphere. So we have some amazing photographs from the International Space Station or high flying satellites that kind of see these reddish glows. So they're not necessarily bolts, but it's the way the electrical activity is happening really, really high up in our atmosphere where there's a lot less air. And what it looks like, it's beautiful, really pretty.
Is ball lightning a real thing?
Yes. So ball lightning, as Chuck was just pointing out, is a real phenomenon. It's just one of those things that is very hard to predict, which makes it very hard to study. There's been a lot of reports. I mean, I've heard people say they saw this ball of glowing, charge moving down the aisle of their airplane. didn't harm anyone. I've heard other accounts of, I saw this glowing ball, like roll through my front door in the middle of a lightning storm. Scientists and just even your average person are not entirely sure what causes it to kind of create that ball shape and move through the air. So it is something that we would love to study more if we could better predict where to find it or how to recreate it in a laboratory.
Jacob, who is 5 years old, wants to know, can lightning cause tornadoes and where the lightning is flashing?
So it's not really a case of the lightning causing the tornadoes as the same thing causing both lightning and tornadoes, which is really big storm systems. So when we get on, say, like a hot summer's day, the sun beating down on our atmosphere, the sun drives all of our weather. The heat from the sun causing our air to heat up and then move around, hot air rising, cold air sinking. What it can do is turn into cycles with hot air going up and cold air going down, and you get a kind of spinning in the atmosphere, in the air, and that up and down spinning can translate into sideways spinning in a cloud, and that sideways spinning, if it gets intense enough, can form a tornado. That same process of air moving around causes tiny little particles in the air to rub against each other and build up electric charge. And so the same storm cloud that might start rotating into a tornado can also have some lightning bolts coming out of it because there's imbalance of electric charges. So it's not that lots of lightning bolts create a tornado, it's that the same storm cloud, because of the same reason, can have some really intense wind, tornadoes, and also lightning, and also a whole lot of really heavy rain, maybe even hail.
Thank you. So we have a couple related questions. Tiffany is 11 and wants to know what comes first, thunder or lightning? And then also, how can you tell how far away lightning is?
I'll take the what comes first question. Where there is lightning, there is always thunder. And the difference between thunder and lightning, and why there is a difference between when you see the lightning and when you hear the thunder, is because of the different speeds of both. The light from a lightning will travel virtually instantaneously. It travels at the speed of light, 186,000 miles per second. So you pretty much see the lightning the instant it's produced. The thunder, on the other hand, is a sound wave that travels through the air, and it travels through a set speed of about 1 mile every 5 seconds. So the farther you are away from the lightning bolt, the longer the delay between when you see the lightning bolt and when you hear it. And that's a good indication, by the way, of how far away the lightning is. If you see a lightning bolt and then 10 seconds later you hear the thunder, you know that the nearest part of the bolt was 2 miles away. But the lightning and the thunder are produced almost simultaneously. The lightning is basically heating the air up to 90,000 degrees Fahrenheit in a very tiny fraction of a second. That air expands like an explosion. So for all intents and purposes, it's virtually simultaneous. But we hear the thunder later because of the time it takes the sound wave to go through the air.
You may have noticed if the lightning bolt and the thunder come very close together, the thunder sounds like one clap. Whereas if lightning bolt was farther away and it takes 10 or 15 seconds before you hear it, it kind of gets that rumbling effect. And that has to do with the fact that sound wave, Chuck mentioned, is moving past trees and houses and cars and all these other things out there in our world. And the sound kind of gets broken up a little bit. So it sounds a little more rumbly than that clap that you would hear. It was right above your head.
Who is Nikola Tesla, and why do we talk about him so much when we're talking about electricity and lightning?
Oh, Nikola Tesla was a brilliant scientist. From the late 1800s, early 1900s, we often talk about him in association with Thomas Edison, who is sort of credited as inventing the light bulb. The two of them were both very smart scientists. Thomas Edison was much more of a businessman, which is why he kind of gets more of the notoriety for things. But so much that we use in our day-to-day lives comes directly from Nikola Tesla's research. The fact that our power grid is based off of what we call alternating current and not direct current comes from some of the patents that Nikola Tesla had. He didn't get the credit. He didn't care about the credit. He was truly a scientist that cared about the science and not really a lick about money. which means he did actually die eventually, a very poor man in monetary senses, but had really rich, amazing science inventions through his lifetime. I don't know if Chuck or Eric have other sort of want to sing praises of Tesla.
Yeah, I mean, in anything from cell phone to power transmission stations, it references and uses technology that he came up with, which was just so groundbreaking for the time that it almost seemed like magic to people that he would show it to.
Radio waves.
Yeah.
Videos.
So lots and lots of things happening in the late 1800s with electricity being understood really at its base level for the first time. And Tesla was right there making all those discoveries and making new inventions with those discoveries.
And one of the things he wanted to do was to see if he could broadcast electricity wirelessly, that is to light bulbs, not with wires. But so he, in Colorado Springs, one of his I see one of you has a question about Colorado Springs. And yes, he did build a giant Tesla coil named after him, which is basically a large transformer that can produce very powerful discharges. And he did make these in various places, not just Colorado Springs, but El Paso. But unfortunately, he had a history of melting down generators and causing power outages and things like that. But he was able to make lights glow at a distance, but not you can't do it worldwide, obviously.
So speaking of generators and other equipment, can we capture energy from lightning that can be used to make our lives greener?
So yeah,
we like to do it.
We like to think of renewable energy resources instead of burning fossil fuels, which are finite and have a lot of environmental problems and contribute to global warming. If we could use the light from the sun, then that would always be there and we wouldn't have as many greenhouse gases from it. If we could harness lightning bolts and turn all that energy in nature into our own energy, it seems like a really great idea. The problem is that even though a lightning bolt is incredibly hot and incredibly powerful, it lasts for such a tiny fraction of a second that it's really not that much total energy in terms of what we need for our modern lives. A lightning bolt could power a light bulb for maybe a couple of minutes, maybe an hour. So if you think about, say, the Museum of Science and how many light bulbs we have and refrigerators and TVs and computers and how much we would need lightning to strike our device that turns lightning into our electricity, we would need lightning to strike the Museum of Science about once every 2.5 seconds for our power needs, which really would be awesome if a science museum just had lightning constantly striking it from the clouds, but there's no way to actually get that to happen. And even if there would, it probably wouldn't be the safest way to get our power. So even though it is theoretically possible, and we have done it, we have gone out and had lightning strike a device that gets that energy and does something with it, it's not a practical way of solving our energy problems for our modern lives.
So speaking of lightning strikes, Benjamin, who is 3 years old, wants to know if lightning can hurt you.
It certainly can. Of course, any sudden discharge of electricity can cause damage to the tissues in your body, can damage your nervous system. And as a matter of fact, people playing golf, when they continue to play golf during a thunderstorm, raising that golf club up over your head has been the last mortal act of many golfers. So you obviously do not want to be in lightning's path. And one of the ways you do that is you don't be the tallest thing around. When lightning is a discharge from the sky, it actually makes a current out of the air, makes a wire out of the air, and it's coming from above, at least the light that we get here in the ground. You don't want to be the first thing that lightning is going to go for. So you don't want to be alone on a beach, or alone in the middle of a field, or you don't even want to be standing next to that tree. Lightning power of a lightning bolt is in the order of something like 3 trillion watts. So here's somebody actually demonstrating what you need to do if you are in danger of being struck by lightning. And anytime you count less than 2 seconds between when you see the flash and when you hear the crash, you are in danger of being hit. So you want to do what this gentleman is doing here, crouching down and not making yourself the tallest thing around. You notice he's also not lying flat on the ground. He's got his feet firmly in the ground. You not only want to make yourself short, but you also want to minimize the amount of your body that is actually in contact with the ground or in contact with a tall tree that you're standing next to, because electricity can always branch, the lightning discharge can always branch out. Some of it could go through you as well as through the ground, and you don't want that to happen. It could stop your heart from beating, stop you from breathing, and a lot of other nasty things.
What is a lightning rod? And related, does every building have a lightning rod? Is there like a code about that?
Lightning rods are sort of interesting when it comes to architecture. To answer that second question, no, every building does not have a lightning rod. They're generally not needed because the likelihood that your building is going to get struck by lightning is relatively small. And honestly, in everyday life, the reason for a lightning rod is sometimes confused. It's not there to get struck by lightning. It's actually there to help prevent a strike at all in the area. The idea of having this pointy metal object that is really high up in the sky and connected to the ground by a ground wire is actually to draw off those extra electric charges from the thundercloud before you get enough buildup of that separation of charge to create the lightning bolt. So they do a pretty good job. We do have lightning rods that are on the tops of tall buildings. Certainly something like the Empire State Building in New York City or the Eiffel Tower in Paris. They are very tall and are likely to get struck by lightning. I'm guessing both of those places do have a lightning rod to help prevent the buildup of that excess charge. But also too, if a lightning bolt does strike, it will safely carry that lightning, that energy directly down to the ground and not affect the building nor the people inside of it. So that's sort of the basic sort of theory behind a lightning rod. I don't know if Eric or Chuck have extra facts about lightning rods.
Yeah, I would say that maybe if we lived in a different atmosphere and lightning strikes were more common everywhere, then it would be part of a building code. It would make sense. But similar to how the building codes for new buildings in California are very intense in terms of being safe from earthquakes, we don't have that in Massachusetts because we just don't get that many earthquakes. So the same thing for a lightning rod. You wouldn't see it on the average house built in Massachusetts because lightning strikes houses in Massachusetts so infrequently that it's not really necessary compared to the cost and the effort that it would take. If you go out to places that are in the Midwest and Tornado Alley, like Kansas and Nebraska, you might have a big barn that's the tallest thing around for miles, and there are frequent thunderstorms there. It's a higher risk, and so it's worth it to put a lightning rod on that kind of building. So it's never required, but it's always a good idea if you live in a place where there's lots of lightning and you're the tallest building around.
I'm sure the weather station on the top of Mount Washington has a lightning rod. Just being that high up in our atmosphere, more likely to get the summer strikes of lightning here in New England. But your average house down here at sea level, not so needed.
So I think we have time for one more question, and I'm going to go with one of our fascinating ones. Does lightning hit airplanes, and what happens?
Lightning does hit airplanes, but the people inside hopefully are it's almost don't get fried. And one of the important reasons for that is the same reason why we can actually do the theater of electricity demonstrations and raise ourselves up in that cage and have the outside of the cage struck by lightning, and we don't get electrocuted. When the type of energy, the type of electric energy from a spark, which is all of a sudden all that current at once, strikes a metal object, it will repel to the outside surface of that object, something called the Faraday effect. And that means that if you are in anything that is a hollow metal object, such as a car is safe, and it's not because of the rubber tires on the car. It's because of the fact that the car is made of metal. When a sudden influx of electricity hits it, it repels to the outside of that metal object. It has to be a metal object, by the way. So that's why you're safe inside of a plane in terms of the actual strike itself. That the problem with planes is that as that electricity passes across the body of the plane, it will knock out the electronics, it will knock out the avionics and other things that are critical to the safe navigation and flying of the airplane. So that is a problem as well. airplanes are in more danger, actually, in terms of the actual flying of the airplane. They're in more danger during a thunderstorm because of downdrafts and tailwinds and features that are related to the air circulation. Lots of planes have crashed on takeoff or landing because they were too low for the changing wind conditions for the pilots to be able to correct for that and to be able to fly out of the danger. But the lightning itself, that has its kind of own set of hazards associated with it. But the metal object, that's why you're safe inside of a car, because of the metal.
I always like to say, to Chuck's point of it might blow out all the electronics on the airplane, I certainly hope whatever pilot is flying my plane is well versed in using manual sort of steering rather than automatic pilot. So generally the planes, on average, a commercial airliner is going to get struck about once a year, and you do not hear about terrible accidents. So that's good news, and you can feel safe flying, even in a lightning storm. And the lightning looks amazing if you're up there in the middle of the clouds.
Yes.
Awesome. Thank you. It sounds like pilots and engineers and scientists have worked together to make sure that we're going to be okay. Well, thank you so much, everyone, for answering all of our questions about lightning. Unfortunately, we are out of time. So at this point, I'm going to ask you all to say your goodbyes.
Thanks, guys. Have a great afternoon.
Great day.
And I would like to thank all of you, our scientists, for joining us today and asking those amazing questions. If you enjoyed today's presentation, you can visit us at mos.org/mosathome to see more of our virtual offerings, including shows like these or even virtual exhibits to check out. And if you'd like to support more of this work, please visit engage.mos.org/welcome. We'll see you next time. Thank you, everyone.